Okay, let's do an example of a low-pass filter, applying a low-pass filter to an image in the frequency domain. So using Matlab, we'll create a filter consisting of ones inside a disk, zeros outside. We'll take the transform of that and the image and apply it to the image in the frequency domain. Take the inverse transform, and then we'll note the ringing here. So here is the program I'll use. Let me get a editor here. Okay, so I'll read in the moon image. Go ahead and run that. So that read in the moon image, I guess I should display that as well. And created a spatial filter of the same size but centered in the middle here. Okay, so now I want to take the transform of that, but the zero frequency for a Fourier transform, remember, is up here in the upper left-hand corner, not in the middle of the image. So I need to shift all this up to there. So the way I'll do that is using MATLAB's function IFFT shift. So let me go ahead and run that. Clear. So the result of doing that moves the center of that disk up into the upper left-hand corner. Since the Fourier transform is considered to be periodic, it wraps around. So I wind up with the other pieces of it in the other four corners. Okay, so now I'll take the Fourier transform of that, of the image, multiply that with the my ideal low-pass filter that I just created. Go ahead and do that. And let's just take a look at that. So as you can see, that is the Fourier transform of my resulting filtered image, where I have zeros outside a certain radius, and then this is the non-zero result inside that. So finally, I'll go back to the spatial domain. And display that. So that is my blurry image as a result of doing that filtering. So notice the ringing. To see that more clearly, I'll use MATLAB's IM profile, which allows me to interactively draw a line to get me the intensities across that line here. So as you can see, through the edge of the moon here, I get a step edge, a blurry step edge with this ringing like that. Okay, another type of low-pass filter is the Gaussian. So the Gaussian is attractive because it doesn't produce this ringing. A Gaussian spatial filter is its Fourier pair is also a Gaussian in the frequency domain. So although we don't have ringing, it doesn't attenuate perfectly high frequencies. And this is a result of applying a Gaussian low-pass filter to an image. Another final type of low-pass filter is the Butterworth. This is kind of a compromise between the Gaussian and the ideal low-pass filter. It has this form here where you define a radius d0, which will be the cutoff frequency. So the value of the filter is 1 over this raised to the power 2n. So as d, for very small values of d, basically we get a 0 here. This term goes to 0, so we have a result of 1. For very large values of d, this result is very large, so the filter goes to 0. So when d is equal to d0, the filter has a value of 1/2. So by varying the order, this little exponent value n, we can make this transition more or less sharp. So in 2 dimensions, it would look like this. I'm showing here the radius where the magnitude of the filter drops 2.5. And as the order increases, eventually this will approach the ideal low-pass filter. Here's a cross-section of the Butterworth filter, the spatial representation, I mean. So as the value of n increases, you can see it looks like a sinc function. So that is the Fourier transform of an ideal low-pass filter, so it tends to look like that. And this is the result of applying a Butterworth filter to these images. Okay, let's look at sharpening filters. So sharpening filter, very easy to think of as just taking 1 minus a low-pass filter. So in the case of an ideal low-pass filter, it looks like a inverted disc. Similarly for a Butterworth high-pass filter and a Gaussian high-pass filter. So here are some results of a high-pass filtering with Butterworth filter and let's see. No, this is an ideal low-pass filter, and this is a Butterworth. Finally, let's look at some applications of frequency domain filtering. One of them is the notch filter. So a notch filter is a filter that rejects or passes specific frequencies. For example, periodic noise corresponding to spikes or lines in the Fourier domain. So the idea is we'll design a filter with zeros at exactly those frequencies that we want to get rid of or enhance. Example would be periodic noise due image mosaics, where we put a bunch of images together to make a mosaic. Scan line noise due to a scanner, or halftone noise as shown here. This is a newspaper image where gray levels are produced by patterns that are very regular like this. So the Fourier transform of this image, you can see these large spikes here corresponding to that periodic pattern. So what we'll do is we'll look at the spectrum of the noisy image, find those frequencies, create a mask image with zeros in those places, multiply that mask with the original to zero out those frequencies, and then take the inverse transform. So pictorially that would look like this. Here's my input image Fourier transform, and let's say it has some unwanted spikes here. So what we'll do is we'll create a mask image that is 1 everywhere except for those 2 places. Then we'll multiply the mask image times our Fourier transform of our input image, and we'll get the transform with zeros at those places. And finally, we'll take the inverse Fourier transform of capital G, and we'll get our enhanced image, or our restored image. So here's an example of doing that for that halftone image. Here we've put notches, which are in the shape of a Butterworth filter, at those spikes, and then multiplying those notches with the input transform and doing the inverse transform gives us the restored image. Let's do an example on another image. I'm going to show a way to do this that shows you don't have to be very careful about this. I mean, when people first started doing this, they actually didn't even use computers. They just used negatives and lenses. But the idea here is I'm going to draw the notches by hand using paint. So this little program reads this noisy image. I'm going to show the transform of it and write it out. So let me grab this. Whoops. Okay, so there's my image. I'm going to take the Fourier transform, and I'm going to shift it so that the values, the zero frequency is in the middle. I'm going to create an image called S, which is the enhanced version of that. And then I'll go ahead and write that out to a file scaled 0 to 1 called mask.tiff. Okay, so now I'm going to read that in using my paint application. So here is paint. There's my image, and you can see the peaks there. So I'm just go ahead and draw zeros on those places, namely black. So, and I won't be too careful about this. Let's see, I need to fill that. Okay, let's try that again. So let's say I fill those 4. Go ahead and write that out. And then I'll read it back in. Paint produces a color image, but I really only want a grayscale image. So I'll take the first band of this red, green, blue image. And then I'm going to threshold this at places where m is greater than 0. So what I've just created is a mask image with zeros at the unwanted spikes and ones everywhere else. And finally, I'll go ahead and multiply and take the inverse Fourier transform of that. So that produces a pretty cleaned up image compared to our noisy original. So the point of this is I just wanted to show that this doesn't have to be too exact, but of course you would get better results if you use, say, a Butterworth filter and also take advantage of the fact that these notches are they should be in symmetrical locations because the Fourier transform is symmetrical. Some other examples, these show other examples of periodic noise due to periodic interference. Here we'll just use a filter, a notch filter that's a line, which wipes out the entire spectrum along these lines here. And that produces this cleaned up result.